Right, so last time we discussed that to talk about areas in R2, rather than talking about the linear span of the parallelograms themselves, it makes more sense to talk about some function which will take in two vectors and then give you back a real number. So the definition that we landed upon was this construction, which is the second wedge product of the dual of our vector space V, which is R2. And so remember what that means is that we have these epsilon I guys, which are elements of the dual space, which is essentially just a linear map from our vector space to R. And then the second wedge part of it is to take essentially formal products of the epsilon i's and take linear combinations of them, modulo the relationships of bilinearity and the alternating property as we've seen before. And the important point of these guys are that each element of the space, which is called the space of two forms. So this guy is the space of two forms. Each two form gives you a map which inputs in two vectors and gives you back a real number. And so this is the formula that we get from it, which is that epsilon 1 is applied to v1, epsilon 2 is applied to v2, and then you flip it around and add a negative sign. And this should correspond to some notion of an area of the parallelogram spanned by the vectors v1 and v2. So generalizing a bit, if we move to Rn, then now instead of just talking about like one and two dimensional objects, we can talk about any k-dimensional parallelepipeds. So anything spanned by k vectors. And so earlier we talked about how we could discuss these volume elements by taking linear combinations of k-dimensional parallelepipeds, but similar to what we did in R2, what we actually want to talk about is something which is a function which takes in k vectors, and then it'll give you some function, or it'll give you some real number, which would be the volume of the k-dimensional parallelepiped spanned by those vectors. And these are known as space of k forms. So formally, it's just generalizing this definition from above. You take V dual, and remember V is Rn, so V dual will also be in n-dimensional space since it's the Homs from Rn to R. And you're taking the kth wedge power of this, which is essentially taking formal products of k elements of your dual vector space, and then module the relations of, instead of bilinearity, multilinearities, which means it's linear in each entry, and the alternating property. So it's the same properties that we saw when we tried generalizing from two-dimensional formal parallelogram elements to k-dimensional formal parallelogram elements in higher dimensions. So most places stop by saying that this is the definition of k-forms, and then they just move on. But what I want to do is illustrate more what this function would actually be, how to generalize this formula, and how to interpret that formula. Because generally speaking, you won't really need to explicitly touch the formulas yourself, but it's good to know how they work so that at least you can be sure that what you're doing makes intuitive sense. So I want to start with um, the maybe the simplest non-trivial case, which essentially has almost all the subtleties. So this will be V is equal to R3. And what we'll do is we'll set K equals 2. So we'll be analyzing the space lambda 2 of R3 dual. So what does this look like? Well, what we can do is we can take a basis E1, E2, E3, and then we can set dual vectors. So epsilon 1, epsilon 2, epsilon 3 are in V dual. And these will be set just as before, such that epsilon I of Ej is equal to delta Ij. So it evaluates on 1 to one of these vectors and then evaluates to 0 on the other ones. And again, because the dual to R3 is again R3, these three span R3. And if we're looking at lambda 2 of it, then it turns out that it will be spanned by epsilon 1 wedge epsilon 2, epsilon 1 wedge epsilon 3, and epsilon 2 wedge epsilon 3. Yeah, so we have three elements of lambda 2 R3 dual, and we can see how each one of these gives sort of an area element, and how linear combinations of those will also give area elements. So, for example, we can start off by saying, okay, what happens if we take epsilon1 wedge epsilon2 evaluated on e1 comma e2? Now, technically speaking, I haven't exactly said what this as a function should be, but really because we're just looking at areas, you can imagine that the function should be the same as the function that we had for two variables, for two vectors in two dimensions. And so this will just be epsilon1 e1 epsilon2 e2 minus epsilon1 e2 epsilon2 e1, which, as we've seen in the last video, is just 1. And what we can also do is we can say, okay, what if we take this guy and we look at e1 comma e3? Well, then that is equal to epsilon1 e1 epsilon2 e3 minus epsilon1 e3 epsilon2 e1. Again, basically by the same definition here. And so then what we see is that e1 epsilon1 e1, that's 1, epsilon2 e3, that's 0, epsilon1 e3 is 0, and epsilon2 e1 is also 0. So this will just come out to be 0. And so this makes sense because essentially what we see is that this epsilon1 epsilon2 is measuring the following. So we have our three vectors. And so in our first case, we took this parallelogram and we're looking at the area of that. And in the area of this E1, E2 plane, this will have an area of 1. But if we look, as in the second example, at E1, E3, which is this plane, which is perpendicular to that, then this plane, since it's perpendicular to this horizontal one, it should not have any area on the horizontal plane, and so we get 0 like we expect. But actually, these notions of so the notion of what area will give if the parallelogram lies in the plane spanned by these guys is basically the same thing as reducing it down to a two-dimensional case and then evaluating it there, which works. But in another case where the two vectors are outside of the plane, then it's a bit more subtle. So for example, what we can do is we can look at epsilon1 wedge epsilon2 evaluated on this sort of diagonal parallelogram, which is spanned by the vectors e2 in this direction, and in this direction e1 plus e3. So we can try evaluating this guy on e1 plus e3, comma e2. And so this will be something which is sort of a 45-degree angle off from the horizontal. And we can see what evaluating this expression on these two vectors will give us and what sort of notion of area this actually gives us in this case. So this will be epsilon1 evaluated on e1 plus e3, epsilon2 evaluated on e2, minus epsilon1 evaluated on e2, and epsilon2 evaluated on e1 plus e3. So it's pretty easy to see that both of these guys will be 0 because there's no matching indices here nor here. For this one, this splits as epsilon1 e1 plus epsilon1 e3. And this guy gives you 1, and this one gives you 0. So in total, this one gives you 1. Epsilon2 of e2 is also 1. So it'll be 1 times 1 minus 0. So this will be 1. So what it's actually doing is it's saying this is at a 45-degree angle from the plane. But what it does is it projects it down onto the plane and then takes the area of the projection. So the question is, since both of these don't lie in the plane, this one does have a non-zero area, while this one doesn't. And the reason for that is if you project this one down, then it'll have an area of 0. Whereas if you project this one down, it'll have an area of 1. So exactly how are we projecting it down? Well, if I look at it from the face where we have E1 and E3, so sort of E2 is into the page here, then the first parallelogram, this guy, would vertically sit over here, while this one would sit diagonally over here. So the projection procedure that's suggested by these numbers is that we project straight down. And in that case, this vertical one will have a projection of just a line segment, which will be this, which will have an area of 0. But this one projected down will be projected onto this area, which will have an area of 1. However, there are other ways that we could project down. For example, what if instead of projecting directly down, we projected sort of diagonally here? So in that case, what would happen is that this one would actually be projected down to a line, which would be the line E2, because we're essentially projecting down on the 45-degree slant. And what would happen to this one is that it will sort of be in the plane, but it'll be projected onto this flipped parallelogram onto the other side. Because if we take this vertical line and project it down 45 degrees, then it'll be spanned by E2 and negative E1. So what that means is that the projection is actually defined. Remember how the dual vectors are defined not just by E1 and E2, but epsilon 1 and epsilon 2 also take E3 into account. Because we have epsilon 1 of E3 is equal to 0. So in this case, if we're projecting down along this diagonal, then what that would really be doing is it would be taking epsilon 1 prime, epsilon 2 prime, and epsilon 3 prime, and that would be dual to these three vectors E1, E2, and this third one, which is E1 plus E3. And if we do that, then we can look at, okay, what is epsilon 1 wedge, or epsilon 1 prime, wedge epsilon 2 prime? If we evaluate this on E1 comma E2, then you can redo the computation here, and you would see that this is equal to 1. And by the way, when I say it's dual to, I mean that epsilon 1 primary value on this is 1, but on the other two guys is 0. Epsilon 2 primary value on this is 1, but on the other two guys is 0. And epsilon 3 evaluated on the sum is equal to 1, but on the other two is 0. So if you want, you can call this E1 prime, E2 prime, and then the sum is equal to E3 prime. So because E1 is equal to E1 prime and E2 is equal to E2 prime, then the area is still 1, which is fine because it says that essentially we changed our basis in some vector which wasn't in our plane. So this shouldn't really affect any area that we compute, which is intrinsic to the plane. However, now if we do epsilon 1 prime wedge epsilon 2 prime, and then evaluate it on the vectors, say E1 and then E1 plus E3, sorry, I should say E2 and E1 plus E3. So this example here, except instead of taking epsilon 1 and epsilon 2, we're taking epsilon 1 prime and epsilon 2 prime. Then what happens is that this is epsilon 1 prime, E2, epsilon 2 prime, E1 plus E3, minus epsilon 1 prime, E1 plus E3, epsilon 2 prime, E2. So this guy gives us 1. This guy, now, because we have changed our third basis vector, this will actually give us 0. And then because epsilon 1 prime evaluated on E3 prime, which is equal to this combination, which is this 45-degree thing, will give us 0. And then similarly, this guy will also be 0, and this one will obviously be 0. So then our resulting area is 0. So what this says is, and you can compute yourself, epsilon 1 prime wedge epsilon 2 prime on E1, E3, I hope at least should give you negative 1. And so that says is that if your two vectors are inside the plane, then it's fine, just evaluate it as if you would taking some area in R2. But if your thing is outside the plane, then what you need to take into account is the other basis vectors, which you are taking the duals of. And so what you do is you essentially project down from those vectors to project down onto the two-dimensional plane which you care about, and then evaluate your area there. So in this case, essentially it's saying that V can be expressed as a unique combination of alpha I Vi for some basis, or I guess I should say EI. And so if you're evaluating epsilon1 wedge epsilon2, then you should only take into account E1 plus E2 and ignore what third basis vector you chose. But it does depend on which basis vector you chose to see what the area you get is. Yeah, and the last thing that I want to discuss is, in general, you can have things which are linear combinations of these. So for example, we can take omega is equal to epsilon1 wedge epsilon2 plus epsilon1 wedge epsilon3, and we can look at what is omega evaluated on E1 comma E2. Sorry, not E1 E2, but E1 plus E3 comma E2. So what this is doing is it's taking this 45-degree plane, 45-degree parallelogram, and then evaluating it on this guy. So remember, these guys are essentially functions. So how we are to interpret this is to say we evaluate epsilon1 wedge epsilon2 on these guys, and then add epsilon1 wedge epsilon3 value on these guys. And you can check that, well, we've already done this computation. This one is just 1, and this one is also just 1. And so what that's saying is that this 45-degree guy, you first project it down onto this plane, and then evaluate its area there, and then that'll give you an area of 1. And then to evaluate on here, because we're looking at epsilon1, epsilon3, project it onto this guy via our third basis vector, which is E1, because E1 doesn't line the plane of, oh, I should have said epsilon2, epsilon3, because E1 is not in the plane of epsilon2 and epsilon3, and so when you project it down onto this face, then it'll still have an area of 1. And so in total, this will give an area of 2. So this is not saying that this parallelogram itself has an area of 2, because as we saw earlier, this was some weird thing where this actually has an area of root 2, but we're getting an answer of 2. But what this is saying is that if you project down into each direction and then you take the sum of the areas, then you'll get 2. Okay, so now that we have discussed the case of planes in R3, I want to shift our attention to lambda 3 R3 dual, which measures, well, okay, so this is the space of 3 forms, and these guys measure the volume elements in R3. So in other words, if we take an element omega in here, then we can evaluate omega on some vectors v1, v2, and v3. And then this will give us some notion of the volume of the parallelepiped that's spanned by these guys. There's lines. You get the picture. So spanned by v1, v2, and v3. So we can start in the same way as we had before. We take some basis, E1, E2, E3, and associated with this, we get a dual basis, epsilon1, epsilon2, epsilon3. Again, so that epsilon I Ej is equal to delta Ij. And now we can ask the question, if we take epsilon1 wedge, epsilon2 wedge, epsilon3, and then evaluate it on 3 vectors, v1, v2, and v3, then what should this give us? And if you remember back in the last video, to contextualize this, this is saying, if we consider the cube spanned by these 3 vectors to be 1, then what would the cube spanned by, or the parallelepiped spanned by v1, v2, and v3 have a volume of? So to answer this, if you remember back what we did in the last video, we said something along the lines of v1 is equal to, I guess, a11 e1 plus a12 e2 plus a13 e3, and similarly for v2 and v3. And then what we did was we looked at v1 wedge, v2 wedge, v3, And we said that this would be some multiple of E1, wedge E2, wedge E3. And this multiple over here would be what this number evaluates to. In order to figure out what that is, what we did was we said, okay, well, let's rewrite this guy, expand it all out. So this would be A11 E1 plus A12 E2 plus A13 E3. So that's V1. And then you wedge it into A21 E1 plus A22 E2 plus the E3 term. And then you wedge this one into A31 E1 and then plus the E2 and E3 terms. So this is just expanding the vectors Vi into the basis and then just putting that all in here. And so this first guy is V1, the second one is V2, and the third one is V3. And so the first index represents which vector we're looking at, and the second index represents which basis vector the coefficient is for. And then what we did was we expand this all out using the multilinearity properties. And for example, we get a term which looks like A11, A22, A33, E1 wedge, E2 wedge, E3. And so this comes from taking the first term here, the second term here, and the third term here. We could also get something like A11, A21, A32, E1 wedge, E1 wedge, E2. This comes from taking the first term here, and the second term here. But remember, these guys, because you have a repeated index, you can flip it around, and you'll get that's negative of itself. So this actually values to 0, and so any term with the repeated second index we can ignore. But you might also get terms like A1, 1, A2, 3, A3, 2, E1 wedge E2 wedge E3, or sorry, E1 wedge E3 wedge E2, which comes from taking the first term here, the third term here, and the second term here. But then this is not exactly E1 wedge E2 wedge E3. What we have to do is swap these two around. And remember that we can do that by picking up an overall negative sign. So this is negative E1 wedge E2 wedge E3. And that overall negative sign corresponds to the fact that the parallelepiped spanned by these three vectors is the same as the parallelepiped spanned by these three, but with an opposite sign. And so what you get is some combination of a product of Aij, like 3 products of them, such that the second indices are all different and the first indices are also all different, times these E1, E2, E3s, and then some negative signs when you have to flip around the coefficients, or the vectors, I should say. And if you work it all out, then what you get is that this is actually the determinant of the matrix A11, and so on and so forth, all the way down to A33 times E1 wedge E2 wedge E3. So if you don't believe me, you can write it all out as an exercise, but there will be too many terms, so I don't want to do it myself. Okay, so let's look at a different way in which we can write these determinant terms in terms of these epsilons and the v's, like we did in the last video. So you'll notice that Aij is just the same thing as epsilon j a vi, because the first index tells you which vector you're looking at, and the second index tells you which component you're looking at. So A12 is V2 of, or epsilon 2 of V1. And so I guess in retrospect I should have flipped the indices, but it doesn't really matter too much. And so we can look at what each of these terms looks like in terms of the epsilon j and vi. So this first term would be A11, A22, and A33. And so this will be epsilon 1 v1, epsilon 2 v2, and epsilon 3 v3. The second term, I'll throw in the minus sign here. So it'll be negative A11, A32, and A23. So I swapped these two around to emphasize that This is the second component part, and this is the third component part. So this will be epsilon 1 v1 again, negative, uh, and then epsilon 2 v3, and then epsilon 3 v2. And then maybe you'll have another term which will look like a3 1, a2 2, and then or let's make it more interesting, a1 2, and then a2 3. And this will have some sign, which I'll determine in a moment. But this will essentially be epsilon 1 v3, epsilon 2 v1, and epsilon 3 v2. Um, so so this one actually would be with a positive sign. And the way that I determined that was the number of sign flips that you do, the number of negative signs, is the number of times that you switch basis vectors. So if we start off in this configuration, what this will be is E3, wedge, E1, wedge, E2. And if we want to get this to E1, wedge, E2, wedge, E3, we basically move across E2 twice. And so that'll give us two negative signs, which will be a positive sign. So there's two things to notice here. First is that we're using each epsilon exactly once, and we're using each vector exactly once. So what that means is that these products are all of the form, the product from I equals 1 to n of epsilon I v sigma I. And so sigma is a map from 1 through n to 1 through n, which is a bijection. Alternatively said, if you've seen this, then sigma is just an element of Sn. And so this is all this saying is that each of these guys is a term which looks like this. And this will have a plus or minus sign depending on the number of times that you switch indices. And in fact, this actually has a name, and it's called the sign of the permutation. And so what this will be is -1 to the power of the sign of the permutation sigma. So the sign of the permutation is the number of times that you need to essentially flip the inputs in order to get back to your original configuration of 1, 2, 3, or if you're working up to n, then 1 up to n. And now what we do is we just take the sum over all sigma in Sn, so over all possible permutations of 1 through n, and we look at this formula. And so if you work this out, and I recommend that you work this out for n equals 2 and n equals 3, and you'll see that this exactly recovers for you the determinant formula. Okay, so I'll leave this formula up here for a second, but now we can move on to the general case, which is looking at lambda k of R n dual. So essentially, this is measuring k-dimensional volumes in n-dimensional space, and we want to see how to evaluate what these k-dimensional volumes are. So let's say that we have an element omega in here. How do we look at what omega of v1 through vk is? So the first thing that you should do is pick a basis, e1 through en of r to the n. And a dual basis, epsilon 1 comma epsilon n of this guy. And so what that'll do is it'll give you some basis vectors e1, e2, all the way up to en. And the interpretation of this is that any k-dimensional parallelepiped, which is spanned by k of these vectors, will have a volume element of 1. So in the case that we had a volume element of R3, we have that a cube spanned by E1, E2, and E3 will have a volume of 1. But in this case that we had earlier, here we weren't looking at the full volume E1, E2, and E3, but we had that the area spanned by E1 and E2 was an area of 1, and the parallelogram spanned by E2 and E3 was an area of 1. But if we look at, for example, 2E1 and E2, then this would have an area of 2. So this is essentially saying which parallelepipeds have an area of 1. The next thing that you do is you say that, okay, omega is in this vector space, and I'll leave it as an exercise to show that the dimension of lambda k of R n dual is equal to n choose k, and it's spanned by the element v, but epsilon sigma 1 wedge all the way up to epsilon sigma k, where sigma is some permutation, or I guess not that, but sigma is a map which takes 1 through k and injects it into 1 through n. So this is just a fancy way of saying is that you pick k different indices, and then you take the wedge of all of them. And in fact, by swapping them around, you can also say that sigma I is less than sigma j. Then, and you take the wedge of those guys. So for example, if n equals 5 and k equals 3, then we'll have terms like epsilon 1 wedge epsilon 3 wedge epsilon 5, or epsilon 1 wedge epsilon 2 wedge epsilon 4, and so on and so forth. So these guys span this vector space. So what that means is that we can write omega as being some linear combination of a sub I, epsilon sub I. And so this will be over the subsets of 1 through n, such that size of I is equal to k. So this will be essentially I is a series of k numbers. And what I mean by this is that epsilon sub I is equal to epsilon of, I guess, if I is equal to I1 through IK, then this, I mean epsilon I1 wedge all the way up to epsilon IK. And these AIs are just coefficients which are indexed by these multi-indices. So you can expand omega as a sum of these guys. And then what you do is you say omega of V1 all the way up to Vk is equal to the sum of AI times epsilon I of V1 up to Vk. And these epsilon I of V1 through Vk, I claim that we know how to evaluate these guys. It's by using the same formula over here, except instead of going up to all the way up to n and choosing these i's, instead what we're going to do is we're going to say that epsilon I, or I guess maybe I should write more explicitly as epsilon I1 wedge all the way up to epsilon IK evaluated on V1 through Vk is going to be as follows. So you take the sum over all permutations in Sk, and then you take the product of from I equals, or I guess I should choose j equals 1 through k of epsilon sub I j of v sub sigma j. And then you multiply it by the sign of the permutation, so -1 to the power sine sigma. This is a messy formula, but essentially what it's doing is, in the two-dimensional case, it's recovering this thing of you expand it out as a sum of two guys, and then you evaluate each sum as follows. And in general, what it's doing is it's saying split it up into a sum of things labeled by multi-indices, which correspond to k-dimensional subspaces spanned by, say, E1, E2, E3, or E1, E3, E5, or E1, E2, E4, and then project these k vectors down onto them using the same procedure by excluding all the other basis vectors, and then evaluate it in that k-dimensional subspace by determinant, which is what this formula gives you, and then take the sum of all that with the scaling factors, and then you'll get omega. So yeah, I'll try to make some practice problems or something uh, so that you can try working through some examples of these. But essentially, everything that we've worked towards has led us to this formula.